Okay, great. So welcome everyone for the last TCS Plus of the spring. Today we have John Wright, and before we begin, let's follow the tradition and go around the table. We have many groups joining today. So we have Bentley Volk, or the ceiling over there. Oh, here you are. Welcome from Caltech. We have, getting there. We have Chin Mei joining from Berkeley, UC Berkeley. Welcome. We have Huck Bennett joining from Northwestern. Hi, Huck. We have Nathan joining from UIUC. And hi, Nicolas joining from CMU. And Simon joining from IRIF in Paris. And Sue Parta joining from University of Ottawa. Welcome to TCS Plus, and Toronto. Welcome. Oh, okay. So welcome everyone. And so as I was saying, today's speaker is John Wright, and John graduated from CMU under the supervision of Ryan O'Donnell. And now he's in MIT in the Department of Physics, I believe. He'll tell us about recent work of his with Natarajan, exciting breakthrough on power of entangled provers. This work was covered, among other places, in the Quantum magazine. So we're very much looking forward to it. So, John, welcome.
Thanks. So I just start talking?
Everyone can hear me? So, currently, I only see myself.
Okay.
We don't see the slides yet.
Oh.
Maybe you mixed up the two screens?
Oh, yeah.
Okay, here we go.
Okay. So I just start talking?
Yeah, welcome.
Cool. Pardon?
Yeah, you can. Please go ahead. Thank you.
Okay, thank you. Title of the talk, based off of recent work, showing that NEEX is contained in MIP star. This is joint work with Anna Natarajan. And before I really get into this, this is going to be like a complexity theory talk. So I kind of want to go back to like what a complexity theory looked like in the 70s and 80s. What sort of questions were people asking? What was motivating them? And then that gives us some motivation for studying these quantum variants. So most basic question that we really study in complexity theory is like, what is the power of a prover and a verifier? And there are lots of different ways that you can formalize this question. The most basic one that we all surely know and love is you have a verifier, maybe they have some sort of language L that they want to compute, and they want to know if this input X is in the language or not. But unfortunately, the verifier may be like a weak little polynomial time machine, whereas L might be a very complicated language. And so they may not be able to solve it themselves. So what we do is we supplement them with the help of a prover who is allowed to be pretty much all-powerful. And the prover and verifier are allowed to interact as follows. The prover can send the verifier a message. So we typically think of this message as a proof pi, that X is in the language L. And this is a complexity class. Again, we all know and love it, NP. Making this a little more concrete, of course, maybe the verifier wants to know if a graph G is three-colorable. And so the proof that they'd be sent is a three-coloring of this graph. And even though the verifier may not be able to compute this three-coloring themselves, with the help of the prover, they can tell whether the graph is three-colorable. So our question, what can a prover prove to a verifier? And the answer is, well, we kind of don't know, actually. This is a big open problem in complexity theory. What is NP? Okay, question 2. Then you could start considering like more exotic prover-verifier interactions. So question 2 is, what can a prover prove to a verifier with interaction? So in this setting, we have kind of a similar thing, except the interaction is no longer one way. So it's not just a one-way interaction from the prover to the verifier. Instead, the verifier is allowed to ask the prover a question, for example. And then the prover can respond with an answer. Maybe based off of that, the verifier asks another question. And they go back and forth for a while until finally the prover sends their final answer, and the verifier is either satisfied that yes, X is indeed in my language, or no, X is not in the language. And this is a complexity class IP for interactive proofs. And we do know the answer to the question. So if you add interaction, then due to work of LFKM and Shamir in the early 90s, we know that IP equals p-space. And since we generally believe that p-space is a much more powerful class than NP, this shows that interaction is actually helpful for helping a prover prove things to a verifier. Then at this point, you can just kind of go like crazy and like extend these models even further. So why just have one prover? Why not two or multiple provers? So now the setting is the following. You have a verifier, two provers, which I'm going to name them Alice and Bob for the rest of this talk. And the provers are not allowed to communicate with each other. Okay, so the only way that they can communicate at all is through the verifier. And so a typical interaction between a verifier and these provers is maybe the verifier asks Alice a question, gets back an answer. Given that answer, maybe they ask Bob a question, get back an answer from him. And this protocol goes on for a while until finally, again, the verifier is satisfied that the answer is yes or no. And this is a complexity class multi-prover interactive proofs, or MIP for short. And again, we do know the answer to this class, this question. If you add additional provers, then you expand the power of IP from p-space all the way to NX, okay? And kind of the idea behind this class is like when you have two provers, you can ask provers questions that the other prover doesn't know. Okay, so each prover now only has partial information, and so it's a lot easier to maybe catch someone in a lie. You can spring a surprise question on Bob and cross-check it against Alice and catch them in lies, and that's kind of the power of this class. So here MIP equals NX, and what is NX? This is class non-deterministic exponential time. So a verifier allowed to run in time 2 to the poly n. And kind of one of the canonical examples of a problem in this class, one of the NX complete problems is the following. You're given an exponential sized graph, and you want to know, is it 3-colorable or not? Okay, so this doesn't quite exactly make sense as a problem statement. So let me give you like the actual version, the concrete NX complete problem. So when we talk about exponential size graphs and 3-colorability, the problem we're actually referring to is this problem called succinct 3-coloring. And in this problem, your input is a circuit C, which encodes a graph G sub C with an exponential number of vertices. Okay. So the way it does so is as follows. Here is your circuit C, and it will have 2 sets of inputs. Each of them is n bits. And the circuit is only size polynomial in n, so it's a very small circuit. But the way you're able to interact with the circuit is as follows. The way it specifies the graph is as follows. So because your graph has 2 to the n vertices, they're in 1-to-1 correspondence with the number of n-bit strings. So if I want to know if u and v are connected in my graph, I just plug in the n-bit encoding of u on the left, the n-bit encoding of v on the right, and then I check, does my circuit output 1 or does it output 0? And then if it outputs 1, then I know that u and v is an edge of my graph. And here, the output, of course, is I should output yes if my exponentially sized graph is 3-colorable. So kind of the idea here is you want to give the prover like an efficient way of querying this very large graph. So you give them an efficient representation of the graph, even though the graph itself is quite large. As I said earlier, this is NX complete. And so because MIP equals NX, 2 provers can actually convince you that this graph is 3-colorable. And that's pretty surprising because this graph is so large, it's exponential size, you can't even read it. So you don't even know what the whole graph is. But in spite of that, the power of 2 non-interacting provers can convince you that it's 3-colorable. Okay, so summary of 70s and 80s complexity. NP, don't know, IP equals p-space, and MIP equals NX. And okay, these, it's not just like fun and games, this is like serious research. Why do we do this? Part of it is just to really study like what is the fundamentals of proofs? What's the power of different proof systems? But in addition to this kind of like loftier idea, this is also responsible for a lot of the kind of concrete research that drives complexity theory today. 2 very good examples are delegated computation and hardness of approximation, which are direct descendants of this line of research. So for example, the PCP theorem is just like the proof of MIP equals NX kind of on steroids. All right, so that's 70s and 80s complexity. But of course, we're not in the 70s and 80s anymore. It's the 2000s. And in the 2000s, everyone has a quantum computer, so we should give a quantum computer to approvers and verifiers. And how do you do this? Well, the standard way is you take your classes. They all have these nice little names, and then you have like Qs in front of them. So you get QNP, QIP, and QMIP. And then these aren't actually like the 100% correct names. So QNP is actually QMA, and QMIP is better known as MIP star. But you can ask similar questions about these classes. And this is kind of an interesting thing of when we're talking about proof systems, it's interesting to ask like, what does quantum add to the mix? Can quantum mechanics prove more things, less things? How does it change things? So we actually have somewhat of a similar story as above. So QMA, again, we don't know. QIP is equal to P space, just like IP, according to Jane et al. And then MIP, you know, if you didn't see the title of this talk, you might suspect that it's also equal to NX because it follows the same pattern. But in reality, we don't know the answer. So we don't know what MIP star is equal to. Okay, so how do you define MIP star? So this is a variant of MIP where you allow Alice and Bob to be quantum. So what does that give them? That gives them the power to have quantum states. So each of them in this model are allowed to have their own quantum states consisting of basically as many qubits as they want. Before the protocol starts, they can entangle their states. So do some sort of operation that entangles the states. And this means that now the states are kind of correlated in a weird quantum-y way. When the MIP protocol starts, of course, they're going to be separated so that they can't speak to each other, but the entanglement remains. And finally, what can they do with their states? Well, in the course of this protocol, they'll want to measure their states and get some sort of measurement outcomes and then base their actions based off of these outcomes. So in this protocol, then, we introduce our verifier. And weirdly enough, actually, the verifier in MIP star is typically classical. So you can actually consider a variant of this where the verifier is quantum, but and what would that mean? That would mean it has like its own quantum computer, and maybe the messages between it and Alice and Bob are also quantum. But that model is actually equivalent to MIP star. So it's just easier to think of the verifier as being a classical machine. Okay, so what does a classical machine do? It will send a classical message to Alice, a classical message to Bob. And now given these messages, Alice is going to perform some sort of measurement on her state. And based off of that measurement, she'll respond with an answer to the verifier. And likewise, Bob will perform a measurement on his state and respond with his answer to the verifier. And the power of this model is that, like I said earlier, these entangled states allow Alice and Bob to kind of correlate their answers. So they can produce correlated strategies that maybe they couldn't produce if they were purely classical. And this means that their strategy space is a lot richer than it is in a classical setting. Okay, just to remind you, the verifier is polynomial time, and so all of these messages, these 4 messages, are just always going to be polynomial number of bits. And of course, since the verifier is classical, they're classical bits and not qubits. This, as I've drawn it, is a 1-round protocol. So when I defined MIP earlier, you know, Alice and Bob and the verifier could talk for many rounds. Here I've just drawn 1 round where you ask one set of questions, get one set of answers, and you're done. And at least for our setting, it's perfectly sufficient just to look for 1-round protocols. So our protocols are 1 round. Okay, and then here is just a standard completeness and soundness definition. So if X is in your language L, that just means you want Alice and Bob. There should be some Alice and Bob who can convince the verifier with probability equal to 1. So I'm going to be considering the perfect completeness case where you can always be convinced. And then if X is not in your language, L, then every Alice and Bob should be able to convince a verifier to accept with probability no more than, say, 1/2. But of course, this constant is arbitrary. Okay, so prior bounds on MIP star. So let me just remind you about MIP, because we know it's equal to NX. And when MIP star was first introduced, it wasn't clear whether it was more powerful than MIP, less powerful. It wasn't clear how they're related. And the reason is as follows. Kind of naively, you might think, well, you know, you're giving your provers more power, so that should help them prove more things to you. But that's only in the good case, when they're actually on your side, trying to help you prove something that's true. It also gives them power in the no case, when they're trying to prove something to you that's false. And so the added power of entanglement, they may actually be able to convince you of a false statement. So as a result, it's really not clear how does MIP star relate to MIP. But in spite of that, about, I guess, 7 years ago now, Ito and Vidic show that, in fact, MIP star is at least as powerful as NX. And the way they did it was they took this MIP protocol for NX, and then they showed it was also sound against quantum adversaries. So they showed that if you're quantum, it doesn't really help against this protocol. Okay, so that's the lower bound. It shows that adding entanglement doesn't hurt. But we don't know, actually. It doesn't say anything about, does it? Like any upper bounds. So yeah, what's the best upper bound we know for MIP star? It's actually pretty embarrassing. So the answer is the best upper bound we have for MIP star is equal to RE. If you remember back to your computability theory in undergrad, this is recursively enumerable. So it's a class of all problems which are reducible to the halting problem. So in particular, this is basically the class that contains the halting problem. So kind of crazily, this means that MIP star, it's consistent with our knowledge that it could actually contain an undecidable problem. We don't know how to roll this out right now. And let me just mention very briefly, why can't we prove anything better? Okay. So how do you generally get upper bounds on these classes? For example, how do we get an upper bound on MIP of NX? Well, you find a way to simulate an MIP protocol. And what I mean by simulate, I mean you kind of you wanna run the protocol maybe on all types of prover behaviors and see if it would accept on a given input. So yeah, it's a quantifier. You have to look at all provers and see if any of them make it accept. And if it does, it's a yes instance. So for an MIP star protocol, you'd like to iterate over all prover strategies and see if any of them make the verifier accept. But you just can't iterate over all prover strategies because, as I said earlier, the provers are allowed to have as many qubits as they want. So a prover can have 2 qubits, 3 qubits, 4 qubits, and so on. And these can all be entangled across the two provers. And so this means that there's an infinite number of strategies to consider. Not only that, we don't really have a good upper bound that says for a given problem, the true prover should only need to share a certain number of qubits. For all we know, there might be some problems that require an infinite number of qubits or something very arbitrarily large. Okay. So that's why we can't do better than RE. We just can't enumerate over the strategy space. And then our result improves upon Ito and Vidic by adding an extra E to the NX. So we show that NEEXP is contained in MIP star. Okay, so what is NEEXP? It's non-deterministic doubly exponential time. This is a time where your non-deterministic verifier is allowed to run in time 2 to the 2 to the poly n. Okay? And NEEXP, by the non-deterministic hierarchy theorem, we know it's strictly bigger than NX. And this shows that MIP star is strictly bigger than MIP. And as a result, this tells us that MIP star is not equal to MIP and gives us a classical quantum separation between the two. Okay, what's a complete problem for this class? Well, just like we had succinct 3 coloring for NX, here we have succinct 3 coloring. It's a pretty ridiculous problem. You'd never consider it naturally, but here it is anyway. So you have a circuit C, and just like we had earlier where a circuit C could succinctly represent an exponential size graph, you can also imagine a circuit C which succinctly represents an exponential size circuit. And that's what's going on here. So the circuit C represents an exponential size circuit C prime, and this circuit C prime is supposed to succinctly represent a doubly exponential size graph, G. Okay, so your question here, like before, you just want to know, is G 3 colorable or not? And yeah, it's pretty crazy. Let's see, is that, yeah. It's pretty crazy because this graph is so large that to even give a name to any of the vertices, so there are doubly exponentially many vertices. So to specify a specific vertex requires an exponential number of bits. So you can't even write down the name of a vertex in polynomial time. And yet what we show is that 2 quantum provers that share entanglement can still convince you that this graph is three-colorable. Okay, so that's our main result. And now I'm just going to move on to the proof. So before I do that, are there any questions? Do we take questions?
Okay. Yeah, we can. If anyone wants to ask. Maybe just one question, John. Are there any issues here with the way you represent the graph? Is it adjacency matrix, adjacency lists? Is that an issue at all?
You're saying, I mean, for the circuit that we have, it is like basically an adjacency matrix. But my guess is no. Typically, when you do these succinct sort of things, there's a lot of choice in the representation that you can have, and a lot of them are just interreducible between each other.
Gotcha.
But that's not a definitive statement.
Because it might be, if you just have the matrix, it might be hard to even find one edge.
Yeah. Yeah, but my guess is that having another representation won't really help you.
Okay.
Cool. So yeah, now let me tell you about how does the proof work. So like I said, I'm going to show you that Neeks is contained in MIP star. But first, actually, I'm going to do like a very brief, like ridiculously high level overview of this old proof that NX is equal to MIP. And remember, this proof is purely classical. There's nothing quantum going on here. But this is going to act as a warm-up for the MIP star protocol. And we're going to use some of the tools from the smaller protocol in our protocol. Okay, so what's a strategy? I mean, how do you show that MIP at least contains NX? This means giving an MIP protocol for the problem succinct three coloring. And remember, this is an NX complete problem. Okay, so we're having this MIP protocol for succinct three coloring. And so your input is going to be a succinct three coloring instance, i.e. just an exponential size graph, like a really big graph. And the most naive thing you could ever think of doing in this case is if the verifier wants to know if this graph G is three colorable, you could just have Alice do the standard NP witness, send it the three coloring of the graph. But of course this doesn't work because like the graph is exponential size, and so the three coloring is exponential bits. And so this is simply too long for our polynomial time verifier to read. But you still kind of want to deliver this three coloring to the verifier somehow. This is a thing you need to tell them. And so what these people do in this MIP protocol is you do something clever. You encode this three coloring that you have as a polynomial f. And I should mention one thing, that the MIP protocol I'm talking about right now is not the original MIP protocol, but an MIP protocol that you can write down that's based off of the PCP theorem. Okay, so the provers are going to find some way of encoding their three coloring of the graph as some sort of polynomial f. And like I said, I'm going to be super high level, so I won't at all tell you what this encoding is going to look like. There's just some polynomial f corresponding to their three coloring. And it operates over finite fields, fq. If you're not comfortable with finite fields, just pretend it's the integers from 0 to q minus 1. They'll work for this talk. And this is going to be a multivariate polynomial. So it takes in m different inputs. And m here will just be a polynomial in n. Okay. So the key thing that you want is the following. When you encode this polynomial correctly, then it's going to be a low degree polynomial. And why do you want this? It's because low degree polynomials have magic properties. And one of these magic properties is that if f is low degree, then it's just easy for the verifier to check whether it corresponds to a valid three coloring. Okay, so that means if you're the verifier, if you know that f is low degree, everything's easy. They give you this encoding, and if it's low degree, you can just check that it's a three coloring. So pretty much all the difficulty in this protocol is testing that f is actually low degree. Yeah, so because maybe the two provers are trying to trick you, and so they're trying to trick you with a polynomial that's not low degree. And so you need to test first that it is low degree before you take their word for it. Okay, so how do you test that a polynomial is low degree? Well, it's done by the totally standard low degree test. And in this talk, we'll be looking at the line versus point variant of it. Okay, so now I'm going to give you like a very, very high level overview of the line versus point low degree test. And again, our goal is to test if our function f is a low-degree polynomial. So our verifier is going to prepare a point and a line. So to do this, first it picks a point u in fq to the m, and then it's going to pick another vector v in fq to the m, which is its direction. And both of these are going to be uniformly at random. And then it's going to set L, its line, to just be the line that goes through U in direction V. So it's a line U plus TV for all T in your field. So, it contains a point U, U plus V, U plus 2V, and so on. So U is our point, and L is our line. And the verifier is going to do the following. It's going to send the line L to Alice. It's going to send the point U to Bob. And it's going to receive some answers, ans A and ans B, from Alice and Bob. And based off of these answers, the verifier can tell if f is low degree. Okay, I specified it in this very nebulous way because at least for the rest of this talk, it won't matter what the answers are, and it won't matter how the verifier checks. But just in case you're curious, hopefully a lot of us know this, but the answer Bob provides should just be f evaluated at U. And then the answer Alice provides should be a low-degree polynomial g on the line L. And then the verifier's check is just to check that g of U is equal to f of U. Okay, so, but this is a totally standard line versus point low-degree test. And like I said, for our purposes, it's not important what the details are. For example, what the answers are or the except condition. All that matters is two things. This is kind of the main subroutine in the NX protocol. So when I talk about this NX protocol, just think line versus point test. And number two, the questions in this test are formatted as a line L and a point U. And one thing to remember is just that this line L and point U, U is a point in fq to the m. You remember m is polynomial in n. So these are both easily specified with a polynomial number of bits. And as a result, this gives us a polynomial time verifier. Okay, so that was the very high-level overview of MIP equals NX. And now we're just going to move on to NEEXP, which is contained in MIP star, and we're going to hopefully use some of these ideas. So how do you show that NEEXP is in MIP star? Well, it entails giving an MIP star protocol for the problem succinct three coloring, which, if you remember, is a NEEXP complete problem. So succinct three coloring is just this doubly exponential size graph. And so we needed to design some sort of protocol for the provers to convince it's a verifier so that this thing is three colorable. And okay, I'm going to just be lazy and just ask, can we use the same protocol as from a couple of slides ago, this MIP equals NX protocol? And this is a protocol where the provers, they want to, they have a coloring that they want to tell you, but instead they encode it into a function f, and then the verifier spends most of their time doing the low degree test. Again, so verifiers, it wants to know if this graph G is three colorable. So it's going to send out a line L, a point U, get back some answers. But there's a key difference, which is that in the old protocol, the verifier was operating on an exponential sized graph. And so the verifier would run in polynomial time in doing this. But if we use the same protocol in this case, then we're running on a doubly exponential sized graph. And so everything should be bumped up by an exponential. So the verifier, for example, should run in exponential time. And these messages, the four messages that get sent back and forth, should be also not just polynomial number of bits anymore, but an exponential number of bits. And again, this is because we're now running on an exponentially larger graph. Okay, so you can view this as one problem. All the messages are too long. But in reality, it's two problems. So we separate out the messages into two types. Number one, the questions are too long. And number two, the answers are too long. And basically, we spend the entire paper fixing both of these. Okay, so we want to fix this protocol so that it has small questions and small answers. So the outline of our strategy is the following. I just showed you a protocol for succinct three coloring, where everything is exponential size. And the first thing we want to do is what we call question reducing. It's where you design another related protocol where the questions, instead of being exponential size, are now only polynomial size. Okay, and having done that, the only thing that's still exponential are the answer sizes. And so then we do another step of answer reducing. So we produce another protocol where now the answers are even brought down to a polynomial n. And now we just have a polynomial time verifier, which is great. So when we do this, step one will be where we use the quantum. And so as a result, this is no longer an MIP protocol. It's not classical anymore. The provers are required to be quantum for this to work. And not only that, step one is also kind of the most interesting of the two steps. As you'll see later, step two is pretty standard, whereas step one is kind of the thing that we bring to the table. So in this talk, I'm going to focus on step one. Okay, so I'm going to tell you about question reduction. And question reduction, yeah, so what do you do in question reduction? So the problem that you're faced with is just the fact that your verifier is asking these exponentially long questions. And if we want the verifier to run in polynomial time, they simply can't ask them. So the key idea here is going to be to not have the verifier ask these questions, but instead to delegate the entire process of the question asking to Alice and Bob. Because they're like the omnipotent provers anyway, so they could probably handle this. So in our picture, the verifier samples an L and a U and gives one to Alice and one to Bob. But now what we want is for Alice and Bob to sample L and U themselves. So we want them to sample these questions by themselves without the verifier. Okay, and then in this dream protocol, then the verifier doesn't even send anything to Alice and Bob. And instead, things look like this. So Alice and Bob will sample L, the line, and U, the point. And then Alice will tell you, hey, if I get the line L, here's the answer I'd give you. And Bob would tell you, hey, if I got the point U, here's the answer I would give you. And now the verifier, you're just given all the information you would have had anyway. And so you can decide to accept or reject. So the hope is that Alice and Bob would tell you what you would have asked them anyway. Okay, and we call this kind of idea introspection. So this is the idea that instead of having the verifier ask the questions, we should have Alice and Bob ask themselves a question. Of course, in your mind, you're thinking probably like the obvious thing, which is, why would your provers ever go along with this? Why would they ever help you out? And that's a good point. They have no incentive, for example, to sample the correct line L and the correct point U. So I'll talk a bit about this more in the next few slides. But what's like the most basic thing that you would need to even allow them to do this? It requires them to have some sort of shared randomness. They need a shared randomness so that they can sample these correlated lines and points. Okay, so let's say we tried introspection via shared randomness. And this is where we might suppose that Alice and Bob have access to a shared tape. Maybe something that looks like this. It's all the bits are random, and they can interpret various blocks of it. Maybe the first block is the point U, and the second block is the direction V. And so what would be really nice is if they use their shared tape for Alice just to measure or to read off the line L, which goes through U in direction V. It'd be great if Bob just told you the point U. And then they're being totally honest provers. That'd be wonderful. But of course, there's no way to force them to do that. And so shared randomness is just simply not enough. Why? Because, well, even if they have shared randomness, how can you check them? They could just lie to you. Even if it says U and V, they could report different things. They could report points and lines that are convenient for them and never ask themselves a hard question. And on the other hand, even if they don't lie, so even if Alice tells you L and Bob tells you U, they can still see each other's questions. So Alice can just look at the first register, and then she knows Bob's point. And then Bob can look at Alice's, or the two registers, and then she knows Alice's, or he knows Alice's line. And this kind of defeats the purpose of having two separate provers to begin with, if they know each other's question. So what this means is that we need some sort of shared randomness, but we need some shared randomness that the verifier can control. Okay, we don't just want to leave it up to the provers. And this is where we bring in the quantum. So the shared randomness that we're going to use are entangled quantum states. What does this mean? We're going to basically enforce that Alice and Bob share some sort of large entangled state. And we want to have some sort of control over the state. And we want to have control over how they interact with the state. And it turns out there are like a variety of quantum protocols which allow us to have exactly this. So there are protocols which can force the provers to share a specific quantum state and to also perform specific measurements on the quantum state. Okay, so what do I mean by a protocol forcing the prover to share a state and to perform measurements on it? I mean that the protocol, it's like an MIP star subroutine. And so you ask them questions, you get back answers. And the point is that with these protocols, they're designed so that if the prover succeeds with high probability, then they must satisfy these two conditions. They must specify, share the specific state, and they must perform the specific measurements on it. Okay? And so if they don't satisfy these two properties, then they would fail this protocol. And so you catch them over there. Okay, so this seems promising. This kind of gives us some leverage on the provers. And really all that we're hoping is that we can find some sort of quantum protocol which roughly corresponds to the line versus point distribution. Okay. So we use a protocol that kind of appeared in the literature before called the polybasis test. This is due to like Natarajan and Vidic in a recent 2018 paper, plus like a modification that we have in our work with me and Anand. I should mention though that like the modification we did is very small. So by far, like the vast majority of the interesting stuff behind this test is in theirs and their work. We just kind of slightly rephrase one aspect of it, which makes it a little more easy for, a little more suitable for our use. So this polybasis test, it's one of these protocols that you can play. And this protocol allows you to command the provers to, number one, share exponentially many entangled qubits. And number two, perform two types of measurements on them. One of them is a measurement I'm going to call a total X measurement, and the other one is a measurement I'm going to call a total Z measurement. And finally, even though you're asking that demanding basically that they share an exponentially large number of entangled qubits, this protocol is only going to have a very small question size. So it's only going to have a polynomial question size. This is very suitable actually for what we're doing because, you know, we're trying to get the provers to sample, we want them to have like an exponentially large shared randomness so that they can sample these exponentially large questions. And that's what number one gives us. Well, we want the verifier to only use polynomial question size. Okay, so to explain this test, I really have to explain to you what does any of this mean? So what does it mean that they share an exponentially many entangled qubits? What are these X and Z measurements? And well, I'm not going to tell you what qubits are, and I'm not going to tell you what X and Z measurements are, because that would take a bit too much time. But I'm going to give you a toy model that kind of represents what's going on with a large set of entangled qubits. So this toy model, it's going to kind of sort of look like what's going on here. And then we're going to be able to use it to show how to simulate the line versus point test. Okay, so this is called the EPR toy model. And you know, this is going to be an entangled state that Alice and Bob share. But right now, I'm only going to focus in on the Alice part. So typically, Alice would have like some qubits, but instead of having any qubits or anything like that, I'm just going to imagine she has something called an EPR box. And the EPR box has two registers, a Z register and an X register. And each register is going to contain a string, which is drawn uniformly and independently at random from the set FQ to the M. So A is going to be drawn randomly from FQ to the M, and then B, which will be in the X box, will be drawn uniformly at random from FQ to the M. Now Alice is not given the ability to actually read A or B, so she can't actually peer into the boxes and see what they are. Instead, we give her a different access model for these two strings. And this access model is in terms of the dot products of these strings with other strings in FQ to the M. So we're going to have written next to A, we're going to have a big table that records all of the possible dot products between A and other strings in FQ to the M. So we'll see what A dot all zeros is. Of course, that's going to be just 0. But also A dot all zeros and 1, and so on. All the way down to, this says A dot all ones, but you know, that should really be A dot Q minus 1, Q minus 1, dot 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 Q minus 1. So how does this work? Well, you just specify a Z that you want to read. And then you look in the corresponding cell of the table, and it will tell you the dot product of A and Z. Okay, so that was the Z inner products, but of course we also have the X inner products. And so these will have all the dot products for the string B. And so if you want to know what the dot product of X dot B is, you just look in the corresponding cell. Okay, so we have two tables of dot products. And there's one additional rule that limits how we can access them, or limits how Alice can access them. And it's a rule that says that whenever Alice accesses some Z dot products, she has to erase some of the X dot products, so she doesn't get to read them. And the formal statement is as follows. When she reads the cell A dot Z, so the Z entry in the Z dot product, she has to erase all of the X entries, which have non-zero dot product with Z, and vice versa. So when she observes X, then she has to erase every Z in the Z dot product such that X dot Z is not equal to 0. So like pictorially, if she reads a Z up here, then immediately she just loses a lot of information about X. And then maybe she wants to read one of these X dot products, so then she has to lose a lot of information about Z. Maybe she wants to read another X dot product, she loses even more information. Okay. I should also mention that I often, when I'm talking about reading these cells, I also refer to this as measuring. So sometimes I'll say that she wants to measure Z or measure X or measure X prime. Okay. So let me run a couple of examples just to get a little used to this notation. So let's suppose that Alice went to her X box and read every entry, the B dot E sub I entry for each I. And of course here E sub I is a standard basis vector, which has a 1 in the ith coordinate. Well, B dot E sub I is just equal to the ith coordinate of B. And since she learns this for each I, she just knows B. She knows the entire string B. Okay, so that's great. She knows the entire string B, but what does she know about A? Can she learn anything about A? Well, any Z that she might want to learn about A, supposing it's non-zero, has some non-zero coordinate, let's say the ith coordinate. And then in that case, Z dot E sub I is non-zero. But since we measured E sub I in the X box, this means that we're going to have to delete this Z. And so actually every A dot Z is erased, aside from the one corresponding to the all zero Z. So you erase every piece of information in the Z dot products, and as a result, you don't get any information about A. Okay, so this sort of thing is something I'll call a total X measurement, because she's measuring everything in her X register, but not seeing anything in her Z register. And total Z measurements are defined similarly. Okay, example number 2. Let's say Alice only reads in the X register, she only reads the entry B.E1. Okay, what does this mean? Well, this means that that any Z entry, she can only learn it if Z1 is equal to 0. And she can't learn it if Z1 is not equal to 0. So a good set of Z's that are 0 in the first coordinate are again just the standard basis vectors. E2, E3, E4, dot, 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 just not equal to E1. So she can read the entries A dot EI for each I not equal to 1. And so what does this mean? Well, she just learns A2 through AM, but just not A1. Okay? All right. So that's just the Alice side of things. What does Bob get? Well, Bob gets his own EPR box, except it's filled with the exact same random A and random B. So for example, if both of them do a Z measurement, they both get A. If both of them do an X measurement, a total X measurement, they both get B. If one does a total X, one does a total Z, then one of them will get A, one of them will get B. And in this case, their answers will be totally uncorrelated because A is uncorrelated with B. But this kind of shows you how they can use these boxes to sustain various levels of correlation between each other. Now, I told you this is like a model for the EPR state and for entanglement and whatever. So let me just tell you 3 reasons why this should look like it's a good model, why it should look physicsy to you. Well, number one, it just kind of looks like it has some sort of entanglement in the sense that Alice and Bob have this shared information of A and B. Number two, it demonstrates this thing called the Heisenberg uncertainty principle. So if you remember the Heisenberg uncertainty principle, it's a statement about particles that are, like, if you know their position, then you can't learn their momentum. And this has a similar thing going on with the Z versus the X. If I learn Z information, I can't learn X information. The final thing is that this is non-signaling. So even though they can use these two boxes to correlate, they can't use these boxes to communicate. And that's a basic property of quantum mechanics. Okay, so that was a very long-winded description of these EPR boxes. And the summary that we have so far is the following. So like I said before, we have this polybasis test. This was a protocol which can actually force the provers to share these EPR boxes. And if we ask them to do total X measurements or total Z measurements, they have to do them. And not only that, even if we do this with M, which is like exponential, the question size is only logarithmic in M, so it would be polynomial. Now, what do we want? Well, we want to use this to somehow force Bob to sample a point U and force Alice to sample a line L that goes through U in direction V. And let me ignore the fact that V should be uniformly at random. Let's just fix a V for now and see how we do it. In fact, let's just fix the easiest V possible, the one that's a 1 in the first coordinate and zeros everywhere else. And let's see how we can use our EPR boxes to force the provers to sample the line versus point. Okay. So I'm going to begin by very suggestively renaming one of the two vectors in my boxes. So I'm going to rename A to U, and B is just going to stay B. Okay, so the verifier is going to tell Bob, Bob's supposed to measure a point. So the verifier is just going to say, hey, do the Z total measurement. Measure everything in your Z register. And then what is Bob going to do? He's going to measure his register. He's going to measure U, and he's going to send it to the verifier. So now the verifier knows the point. Now, okay, we did the point. Now we got to do the line. So we want to learn L, which is U plus T times 1, 0, 0, 0. And we especially want Alice not to learn the point U, okay? So one thing we could do is just, again, tell her to do Z total on her Z register, but she would learn U. I mean, she'd be able to use that to learn the line as well, but she'd learn too much. So we have to prevent her from doing that. So what are we going to do? Well, it turns out learning this line L is equivalent to only learning the values U2, U3, all the way through UN. What do I mean by that? Well, the points in line L are all of those that agree with you on the values 2 through M, but they may disagree with you on the first value. In fact, you'll have every single possible value for the first coordinate somewhere along this line, but every other coordinate will be specified by U's. So if I just learn U2 through UM, I learn what the line is. And then if I prevent the prover from learning the value of U1, then you prevent them from learning what U is. Okay, so how do we do this? Well, we're just going to do basically what we did in the second example. What we do is we want her to measure U2 through UM to learn the line. But we also want her to measure B1, the first value in B. And the point is that, as we saw earlier, once you learn B1, then you're not able to learn anything about the first value of U. Okay? So this prevents her from learning information about U1. Okay, so we're going to ask that she measures B1 and then U2 through UM, and we're going to ask that she gives them to us. So U2 through UM will specify her line, and B1 will just be her proof that she measured this thing that prevents her from knowing U2 or U1. But of course, what we're asking her to do is not a total measurement of X or Z. So we don't know how to check that she acts honestly yet. Okay, we don't automatically get that. So well, now the checks that we can do to make sure that she's actually reporting honestly are pretty simple. So half the time, we're just going to tell Bob to measure his whole Z register. That will give him the entire string U, and he has to report it honestly. And then we can just check her UIs against his. And because he plays honest, she has to play honest. The other half of the time, we're just going to tell Bob to do a total measurement on his X register. And then he'll have to give us the entire string B. And then we can just check her B1 against his. Okay, and so this enforces that Alice learns the line. She tells us the line, but then she also erases the first coordinate of B. All right. So that was for the specific direction of 1, 0, 0, 0. Let me give you the general direction of D. So again, the verifier, you want to sample a point and a line. The point that we're going to sample is just going to say, hey, Bob, measure the entire Z register. We got that point U. And then we want Alice to just learn the line L, which goes through U in direction V, but we don't want her to learn U. So again, the way we're going to do this is we're going to force her to measure some value in the X register that will prevent her from learning U, but will still allow her to learn L. And this is like a fun little exercise you can try at home. It's some basic linear algebra that there's like one value we should get her to learn, and that's exactly the value B, inner product B. And if we can guarantee that she measures this value, then we can guarantee she doesn't know U. And this allows us to make sure that they both sample points and lines. Okay, so that's the question reduction. Let me just summarize what happened. So we had this introspection where instead of us sampling these very large questions, we just want the provers to do it for us. And so what do we use? Well, we use two quantum properties very strongly. So first, we use entanglement to give them shared randomness so that they can jointly sample from the line versus point distribution. But then we use the Heisenberg uncertainty principle to hide information about each other's questions. And this allows us to simulate their large questions. I should mention, so earlier I was telling you, hey, this protocol, just like pretend it's only line versus point. But really, there are other questions that are also interesting in the succinct three-set or three-coloring protocol. But similar ideas will work for those questions as well. And after you do all this work, it will establish that NEEX is contained in MIP star with number 1, polynomial question size, and number 2, exponential answer size. Okay, so now answer reduction. This will be very short. So answer reduction, just restating what I said at the end, we have the succinct three-coloring protocol, where the verifier wants to know if circuit is in succinct three-coloring. And so now Alice and Bob, they share entanglement. Okay, so they have two entangled states. And the verifier is going to ask them some questions and get some answers back. And now it's like, I don't even care about line versus point. This is just a general structure of a protocol that you can imagine. And because we did question reduction, we now know that the questions x sub a and x sub b are only polynomial length, even though the answers are exponential. Okay, so the problem, which is obvious, is that the answers AA and AB are just simply too long for a verifier to read if they're going to be polynomial time. And so the solution is pretty simple, actually. We pretty much apply PCP technology like directly to what we're doing. So in other words, like instead of reading the entire strings AA and AB, what we want the provers to do is just compute a proof that their answers satisfy the verifier's checks. And not just any proof, but a probabilistically checkable proof. And the great thing about a probabilistically checkable proof is that you don't have to read the entire proof. So even though the proof might be exponentially long, with a probabilistically checkable proof, you will only have to check a small number of positions. And so what the verifier now will be expecting for its answers, rather than the long answers, will just be the bits of the probabilistically checkable proof that it wants to spot check. And this allows us to reduce the answer size from exponential down to polynomial. And this gives us that MIP contains, or MIP star contains NEEX.
John?
Yeah.
So who chooses those query points for the PCP?
Right, so the verifier will choose the query points for the PCP.
So that's something that has to be included in the first question in the X.
Yeah, so what will happen is in the first question, you'll send X sub A and then maybe like an index into the proof. Now you have there's some difficulty because maybe you tell the verifier, sorry, maybe you tell Alice that, hey, I want to read some indices of your proof. but then there's nothing saying that Alice actually has to tell you those indices are the proof. So there's some additional complication that's not new to our paper. It was previously done in the paper of Natarajan and Vidic, where you actually have to, for some reason, you have to encode the proof in an error correcting code. And then you have to run a low degree test on it. But yeah, so we'll add in the indices into the verifier questions.
Now, isn't there also an issue of the circuit size used to verify the answers? I mean, PCP takes care of the succinctness of the proof checking, but the circuit is still there. It might take a very long time to compute what you actually want to ask.
Good, yeah. So you're saying that like maybe the verifier, the way it checks the answers is with like a gigantic circuit,
right?
Because it has to, because the circuit, the answers themselves are gigantic. And so we actually don't check with a circuit, we check with the Turing machine. And so the Turing machine can just be just like succinctly described. And the point is that we use not just any PCPs, we use a PCPP that has an efficient verifier reduction. So not only does it shrink the answer size, it also, or not only does it shrink the amount of bits that you have to check, but it also shrinks the complexity of the verifier from exponential to polynomial.
So it really depends just on the size of the Turing machine, not the running time, even if it's exponential.
Oh, it depends on the running. So the Turing machine size is just going to be, it's going to be some fixed constant, independent of anything else. So the size of the Turing machine is not an issue. It's the running time of the Turing machine that you care about. So you want to reduce the running time of the Turing machine from exponential down to polynomial.
Thanks.
Yeah. Unfortunately, this was like something that was considered in the PCPP literature back in like mid 2000s. Okay, so that's answer reduction. Like I said, this part is a bit more standard than the first part. Okay, so let me just briefly tell you about some future directions. So one way you can view our protocol is as a compression scheme. So we took this big protocol, big in some nebulous sense. It had big questions, big answers, the verifier ran an exponential time. And then we used some sort of thing to compress it into a small protocol where everything is polynomial number of bits, polynomial runtime, whatever. So this idea isn't really new to us, actually. This idea was kind of inspired by a previous paper of Zhengfeng Ji, who gave a similar compression algorithm for a related MIP protocol, the MIP star protocol for NX. And his compression protocol showed how to convert that bound into another bound on NEEX, just like us, actually. So he showed that NEEX is contained in MIP star, except with this additional parameter, the gap. Okay, so what is the gap? The gap is how close to probability 1 the provers can convince you, even in the no case. So what this says is that in this protocol, even when you're supposed to say no, the provers can convince you with probability 1 minus 1 over poly n time. Okay, so this is why it's not quite MIP star, because with MIP star, you want the gap to be a constant, which is what we established. But anyway, it was a great result. And after this result, Zhengfeng joined some other people, and they basically wondered, like, why do one level of compression? Why only compress a big protocol to a small? Why not start from a very big protocol, compress it to a big one, and then compress it again to a small one? And that's exactly what they did. They found a way to rinse and repeat and make it so that it could recursively call itself. And so then they got like bounds. Each one, they deal with like more and more comical looking classes. So not even NEEX, but like NEEX, which is contained in MIP star with a gap of 1 over exponential in it. Then they're like, hey, if you want 4 E's, we can do that too with 1 over doubly exponential n, and so on. They went all the way down. They got, they did some like infinite level of compressions and things like that. It's a very cool paper. But that's in the case when your gap shrinks every time. But of course, in our protocol, we don't, at least in our one step of compression, we don't shrink the gap. And so you might ask, what happens if the gap doesn't shrink every time you compress? So this is called gap-preserving compression. And the answer here is that what they showed in this paper is that if you had a way to compress the MIP star protocols without shrinking the gap, then 2 things would follow. It's like a close approximation to what's in the paper. But anyway, number one is that there's an undecidable problem in MIP star, which is great. And number two, there's this problem of approximating the value of non-local games, and they would show that this problem is undecidable. So number two, and kind of number one as well, refute something called Tyrolson's conjecture, which basically, other ways of phrasing it, says that approximating the value of non-local games should be decidable. It's one of the big open problems in like entanglement theory. And in refuting that, you also refute something called Kahn's embedding conjecture, which is one of the major open problems in operator theory. So, our protocol kind of looks like this, right? We can compress without shrinking the gap, but it doesn't quite fit. And the reason is that we don't know how to recursively compress it. So we showed exactly one protocol that we can compress down, but we don't know if we could then further compress that protocol down. Like, we really use the structure of this MIP contains next protocol. So all I can say is we're working on it, and I really feel this is like, I don't know, the thing to do right now in MIP star. Like, it kind of just feels to me like the race is on to refute Kahn's embedding conjecture at this point. So I think it's like a very exciting time to be working on this problem. All right, so that's, future directions. That's all I have to say. So thanks for listening.
Thank you, Don. We can take some questions. Still have a few minutes. Anyone? It's all very clear. Let's give people a few more seconds. Is there is there an easy way to derive that shrinking gap result from your paper, John?
Oh, the one that if you shrink the gap. Oh, you're saying like if I wanted the shrinking gap thing, is there a simpler proof that doesn't go through our entire proof?
Yeah, maybe it's more directly you can see it, but you still need to get a succinct.
Yeah. I don't know actually. Let me think. Yeah, I can say at least that like tools that they use in that paper are very different. So it's a totally different style of MIP star protocols. So it's not like we just do theirs, but like souped up. Yeah, I don't know off the top of my head.
Yeah, you can turn off the screen share. At least we get to see you.
Oh, okay.
Probably before. Oh, great! You're actually here. And maybe I should have asked this before, but how close is this EPR toy model to the actual entanglement EPR? I mean, how much have you been cheating here?
Not much actually. So the things that I mentioned are there's a certain, I don't know if you're familiar with observables or not, but the model that I mentioned is essentially exactly the observables that you can measure, the X and Z observables that you can measure on EPR states. And it so happens that these X and Z observables are, let's see, what do we call them? I mean, some of them are non-commuting, so you can't measure them at the same time. And the condition that I gave on the dot product exactly tells you when these X and Z observables commute and don't commute. I should say that actually, like, going from the intuition of the toy model to actually proving that this stuff works is much more difficult. But at least the intuition, like, I think it will never fail you. It will never let you down.
Is there an obvious next step, like a group that's like the poly group but slightly bigger? Or would you have to go through compression?
Oh, let's see. You're asking, like you want some sort of thing that guarantees not just poly measurements, but something better than poly measurements?
Maybe it's vague, yeah.
Well, let me tell you one thing that is slightly related to that, that I think should be true. I was going to mention this as an open problem, but I forgot to add the slide, which is this protocol, it has a question complexity that is polynomial, even if you do an exponential number of, even if you certify an exponential number of EPR pairs. And I think we believe that instead of polynomial, you should be able to have a question size that is constant. So possibly even with like a constant number of questions, you can certify an arbitrarily large number of EPR pairs. That result may follow from some sort of compression thing, but yeah, I think that'd be a very interesting thing to prove.
Okay, so if there are no questions, so thanks, I thank everyone, and thank you, John, for giving this last talk of the semester. Thanks everyone for being with us this year. Hope to see you again in the fall. And I also should thank the co-organizers. This is the credit minute. Gautam Kamath, Nindya Day, Clement Canon, Thomas Vidic, and Ilya Rosenstein, all helping. We're doing all this together already for, I don't know how many years, 5 years. So hope to see you again in the fall. And let me take us offline. Everyone is welcome to stay and chat offline. So thanks again, John.
Thanks.
So in the